Alright, so we're going to talk about Chapter 17, chi-square tests, the goodness of fit, and the test of independence. Thus far, we've only talked about parametric tests. And because these tests all concern parameters and require assumptions about parameters, they're called parametric tests. Another general characteristic of parametric tests is that they require a numerical score for each individual in the sample. Often, researchers are confronted with experimental situations that do not conform to these requirements. In these situations, it may not be appropriate to use a parametric test. So when we have assumptions of our test that are violated, if we go ahead and interpret our findings, they may lead to erroneous interpretations. There are several hypothesis testing techniques that provide alternatives to parametric tests, and these are called non-parametric tests. Occasionally, you'll have a choice between using a parametric and a non-parametric test. In most situations, the parametric test is preferred because it's more likely to detect a real difference or a real relationship. However, there are situations for which transforming scores into categories might be a better choice. It may be simpler to obtain category measurements, or the original scores may violate some of the basic assumptions that underlie certain statistical procedures. The chi-square test for goodness of fit uses sample data to test hypotheses about the shape or proportion of a population. The test determines how well the obtained sample proportions fit the population proportions specified by the null hypothesis. So how is this similar to a test we've already learned? The one sample t-test uses a sample to test a hypothesis about one parameter. This is also, the goodness of fit test is also known as the one sample case. It indicates whether or not the observed frequencies are a good fit to the expected frequencies. There is only one variable and it contains two or more categories. The observed frequencies are obtained through data collection and the expected frequencies are given. Data is measured at the categorical, either the nominal or ordinal level. So the null hypothesis could be that there is no difference in proportions. We use this in situations in which researchers want to determine whether the proportions differ from one category to another. Or we use this, we can say there's no difference from known population. So we use this when a specific population distribution is already known. For example, if we know that 28% of licensed drivers are younger than 30 and 72% are older, we would test against those known population parameters, or population proportions. The observed frequency is the number of individuals from the sample who are classified in a particular category. These are the ones we actually go out and count. We sample 100 people, we ask them a question, and we put them in one of these categories. They can only be in one and only one category. The expected frequency is the value that's been given in the null hypothesis. The expected frequency defines an ideal hypothetical sample distribution that would be obtained if the sample proportions were in perfect agreement with the proportions specified in the null. Data. So the formula for chi-square involves adding squared values, so you can never have a negative. All chi-square values are 0 or larger. When the null is true, we expect our chi-square values to be small. And the bigger the difference between the observed and the expected, the larger the chi-square value and the more chance that it will be significant. I'm going to show you the formula but a little bit later in the presentation. So this is what a chi-square distribution looks like with 1 degree of freedom. This is the critical region here. This is for a one sample case. But as you can see, as your sample size increases, the distribution becomes more and more normal, which is why the central limit theorem works and we can do the statistics that we do. Just wanted to show that to you. In this study, students were asked, so here's an example of a goodness of fit study. In this study, students were asked if they love, like, or hate statistics. The observed frequencies were obtained from the data collected and the expected frequencies were obtained from another source providing the student population frequencies. Given the following data, determine whether there exists a goodness of fit between the observed and the expected frequencies. Research question. Are students' feelings about statistics similar to student population feelings? So the null is that there is no difference from the known population proportions, and the alternate is that there is a difference from the known population proportions. So we have like, love, and hate statistics. And here, the observed frequencies, we went out and asked 100 people, 14 like it, 23 love it, and 63 hate it. The expected from some other study or something that we, some previous knowledge that we have, most likely based on some prior research, would be that 10 like it, 20 love it, and 70 hate it. So we want to know, how well did our sample fit these expected frequencies? We're close. We're really close. So I would imagine that it's probably not going to be significant, but we'll see. Here, each cell in the observed row represents the cumulative counts of each singular person on each of these categories. So you have to be unique. So this person who liked it can't also love it, right? So these are 14 individual people who like stats, and these are 23 who love stats, and these are 63 who hate stats. The easy way to work with these data is likely the way it will come off in Qualtrics, and I'm going to talk more about this in the later in the slides. But they're coded 1 love, 2 like, or actually I have it the opposite. 1 is equal to like, 2 is equal to love, and 3 is equal to hate. Okay, so like, love, hate. See, I have it here. And so here we have one row of data where all of these people say they like stats, these people say they love stats, and it goes all the way down to 100. And here's our contingency table. If I ran a quick frequencies, and we always look at the valid percent, we have 14, 14, 23, and 63, 14, 23, and 63. All right, so how do I do it? I go to Analyze, come down to Non-Parametric Tests, and come over to One Sample. Okay, this box, once I let go here, this box will pop up. I'm going to click Fields, and what will happen is you most likely will have this moved over for you, but if it's not, I want to make sure that the nominal variable is in my test field. So you just make sure it's moved to the test field, and then we're going to click Settings. And since not all of them are equal, so it's not 33, 33, and 33%, we have 10%, 20%, and 70%, we're going to customize our stuff. So we click Customize Test. We want to use the chi-square test. We click Compare Observed Probabilities, and we click Options. Now here we have our table up here. So what I do is I click Customize Expected Probability, and I say Category 1, the expected is 10. Category 2, the expected is 20. Category 3, the expected is 70. I've got 10, 20, 70. I click OK, it takes me back to that other page, and then I click Run. And the first bit of output will get this, and it'll tell you what to do. It gives you the decision. So it says retain the null hypothesis, so there is no significant difference. This is not less than 0.05. P is not less than 0.05, so we fail to reject the null, we retain the null. And then we need this information for our reporting. We have 100 in our sample. We have 2.75 was our chi-squared statistic. We have 2 degrees of freedom, and here is our sig. It says asymptotic sig, 2-sided test. Don't worry about the asymptotic. We're just going to use this as our p-value. And then it gives us some more pretty tables. You can see that there's not a big difference between our expected and our observed, either here or a little bit here. And then it just gives us this bar chart, which I gave you in the slide, but it's totally not necessary. Anyway, results of the chi-square, and this is Greek letter X, Greek letter X squared, goodness of fit test, chi-square, and then we do our parentheses, we put the degrees of freedom first, comma, and then our sample size, then we give the chi-square value, and then we give the p-value. And since p is greater than 0.05, the null hypothesis is not rejected, and therefore the theory is empirically supported. In other words, the feelings of students towards statistics are similar to those stated in the population. Okay. Going forward, now we're going to talk about the chi-square test of independence, which determines whether there is an association between categorical variables, whether the variables are independent or related. It is a non-parametric test. It's also known as the chi-square test of association. So either they're independent of each other or they're associated with each other. The test utilizes a contingency table to analyze the data. A contingency table, also known as cross-tabulation, cross-tab, or two-way table, is an arrangement in which the data is classified according to two categorical variables. The categories for one variable appear in the rows, and the categories for the other variable appear in the columns. Each variable must have two or more categories, and each cell reflects the total count of cases for a specific pair of categories. So it's kind of like correlation, where 1 point is equal to that person on two different scores, the same with this contingency table. It's used to test the following: statistical independence or association between two or more categorical variables. It can only compare categorical variables. Can't make comparisons between continuous variables or between a categorical and a continuous. Additionally, it can only assess associations. It can't provide any inferences about causation. So it's like correlation here. Just because they're related doesn't mean one caused the other. And then if you have a pre-test, post-test situation, the chi-square test of independence is not appropriate. You have to do this McNamara test. We're not going to cover that in this class, but it's easy to run if you Google how to do it. It's very similar. You just click a different box. Anyway, so the data requirements require two categorical variables. There are two or more categories for each variable. We're looking at the we have to have independence of observations. There's no relationship between the subjects in any group. They're not paired like pre-test or post-test. You need a relatively large sample size. The rule of thumb is that the expected frequencies should be at least 5 for the majority of the cells. So here's our null hypothesis. Variable 1 is not associated with variable 2, or the alternate, variable 1 is associated with variable 2. So how is this like what we've already learned? It's kind of like somewhere between an independent t-test if you're looking to see if they're different, and it's also kind of like correlation if you're looking to see if they're the same or associated. All right, so briefly before we go farther, I just kind of want to show you the equation that the computer uses to calculate the chi-square statistic. So what it is this is the observed frequency minus the expected frequency. Take that value and square it, divide by the expected frequency, do that for each of these cells, and then sum them. And so how do we get the expected frequency from the data? So we have 200 individuals here. They're either male, female, Democrat, Republican. So you can only be in one of these categories. You can either be male and Democrat, or male and Republican, female and Democrat, or female and Republican. And so the way we find the expected frequency is that we take the row total times the column total over the grand total. So for this particular cell here, we found in our data collection that we had 25 individuals who were men, Democrats, and what we found was the expected frequency there would be 42.5. Well, how did we find that? We took 85 times 100 divided by 200. And we did that and got 42. Also note that the way you find the degrees of freedom is that you take the row minus 1 times the column minus 1. Well, here we only had 2 rows and we only had 2 columns, so the degrees of freedom is 1. But you can have more than a 2 by 2 table. You can have 2 by 3 or 3 by 4 or whatever. So the degrees of freedom is calculated this way. So there are 2 different ways in which your data may be set up initially. The format for the data will determine how to proceed with running the chi-square test of independence. At minimum, your data should include at least 2 categorical variables represented in columns that will be used in the analysis. The categorical variables must include at least 2 groups, and your data may be formatted in either of the following ways. So if you have the raw data, so each row is a subject, and this is the way it'll come off in Qualtrics. So item 1, this person is a person, 1 ID number, that person's a non-smoker and he's male. This person is a past smoker and she's female. So each row in your data set represents a person on 2 different variables. The dataset contains at least 2 nominal categorical variables, string or numeric, and they must have 2 or more categories. But what if we just are given this, the contingency table, and we don't want to have to go in and input 149 people that we code as non-smoker on one variable and code as male on the next? I mean, that's 400 people that we would have to go and create 400 lines of data. If you're just given this, you're not out of luck. There's a way to do it, but it's a little bit more complicated. So if you have the frequencies, and each row in the data set represents a distinct combination of the variables, we can go in and make this. But the way you do it, so we're gonna tell the computer to create this contingency table. So we have non-smoker, so this person's a non-smoker, and he's male. So we say non-smoker, and we type male, and then we write 149 because that's how many there were in that box. Then we do non-smoker female, so that's this box, and we say 148. We do past smoker, so now we're moved over here, we're 13, past smoker, male, 13, past smoker female, 24, current smoker, blah, blah, blah. We got it. And then we code it. 1, 1, 1 is non-smoker, so 1, 1, 1, 2, so male, female, 2, 2, that's past smoker, and 3, 3, that's current smoker. And we do 1, 2, 1, 2, 1, 2, because this is male, 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 female, female, female. And then you have to go in and put your frequencies. So the way we do that is before we go in, we type all this in, and then we have to go into the column that says data, and we scroll all the way down to the bottom, and we say weight cases by frequency, and then it will make this contingency table for us. Okay, I didn't show you that, but you go to data, which is kind of over to the left-hand side. You come all the way down, and it'll take you to weight cases. Frequency will be here, but you have to click this radio button, and then you bring over frequencies, and we say okay. And then you can go and do a quick frequencies and check that your frequency or your crosstabs looks like the original crosstabs. And if it does, you've done it correctly. Okay. All right, so let's do an example. Is there an association between gender and smoking? So our null is that there is no association between gender and smoking, and our alternate is that there is an association between gender and smoking. You go to Analyze, like we do for everything, go to Descriptive Statistics and click Crosstabs. It'll bring up this dialog box. The first thing we're going to do is we're going to go in our list of variables, we're going to bring over smoking to our rows, and gender to our columns. We could have done it the other way around, but this is the way I've done it. The first thing we're going to do is we're going to click Display Clustered Bar Charts. Then we're going to come over here and we're going to click Statistics. We're going to pick chi-square, and we're also going to do phi and Kramer's V, which is our effect size. Then we're going to click Continue, and then we're going to click over here Cells, and then we're going to click Expected. Observed will already be given. We're going to go ahead and pick our expected, and we're going to do row percentages. And then we're going to say Continue, and then OK. And first we'll see that the clustered bar charts show consistency between the genders pretty much on smoking and the expected and the, between the genders and whether or not they smoke. So the chances are that we probably won't see an association between gender and smoking. So then we come down here and we check the significance, and we see that the significance is 0.205, so it's not less than 0.05. So we fail to reject the null. And then because I had asked for the expected count, I can compare and look and see where there is a difference. Well, because we don't have significance, these are pretty close. But if we had significance, you would see a pretty marked difference in one of these. This is kind of like doing the LSD post-hoc when we do an ANOVA, like, okay, so there's a difference, but now where is the difference? This will tell you. So the results indicate that there is no significant association between smoking and gender. Here's my chi-square, 2 degrees of freedom. Got that from here, 2 degrees of freedom. N of valid cases is 402. Our chi-square value was 3.17, and our p-value is 0.205. Okay, and then I should have written the Kramer's V here. Phi and Kramer's V are going to be the same when you have a 2 by 2 table. Typically I report the Kramer's V, but it's okay to do the phi either way. when you have 1 degree of freedom, this is the range. When we have 2 degrees of freedom, this is the range, etc. Okay, and you can also go to Vassar Stats, this website, if you want to double check that you've entered your data the correct way. You can do this and it'll give you a chi-square value, and it'll also give you the Cramer's V. You can do this and check it against SPSS. I made these slides before SPSS changed and gave you the V and Cramer's V, but you can always do this and just double check yourself. All right, so let's do another one. The research question is there an association between living on campus and class rank? And the null is that there is no association between living on campus and class rank, and the alternate is that there is an association between living on campus and class rank. For this, all we do, the same check boxes, put the rank upper and under in the rows and live on campus in the columns. And here we see a difference with the underclassmen, right? So on campus, off campus, there's pretty, about half, and then here way significantly different. So I think we're going to see a significance here. Because this is a 2x2 table, we get a little more output, namely that Fisher's exact test, which gives you the p-value only over here. We see that there is a significant association between rank and on and off campus. So we state the conclusion. The results indicate that there is a significant association between rank and on and off campus, and we write it out. So we also have this thing called the chi-square test of homogeneity. This is the same test as the test of independence, performed the same way. The difference is in the semantics. Instead of testing whether or not there's independence between the row and the column variables, here we're testing the hypothesis that the different populations have the same proportion of some characteristic. So I'm not going to give you a data set, I'm just going to give you a word example. So in a study of eating habits of children, a nutritionist selects a random sample of 300 first graders, 150 boys and 150 girls. Each child is asked how many times they eat fast food. 1 time a week, 2 times a week, or 3 or more times a week. So the null would be that the proportions for each choice are the same between boys and girls, and the alternate would be that at least one is different. We do the statistics and we find that they are different, so we report out our statistics and we would conclude that the proportions for each choice are not the same for boys and girls. Okay.